Our next presentation is from Nemanja Kamenica, and he's going to be talking about expanding production remotely or to a public cloud. Nemanja is joining us from Cisco and really knows what he's talking about, so I'm looking forward to this. Take it away.
Thank you. Hello, everybody. So, as Wes said, I'm going to talk about expanding kind of live production remotely and how you can do this. But before we go and dive in those use cases, I'm going to explain a couple of other things. So, first, deployment scenarios, how you would deploy that IP infrastructure, where, how, what is benefit of each of them, and then how you can create that remote production. So how you can slowly scale down and then how you can completely do it remotely. And then hit a couple of other use cases, use case of contribution, distribution, handoff to a public cloud, and then importing and decoding that same signal in your environment. So with that, let's look at deployment scenario. The number one. So on the left side, I do have spine and leaf architecture. It's not necessarily a regular spine and leaf because you wouldn't connect anything to the spine, but in deployment, in certain deployments, you may have somebody connecting to the spine. Reason is usually that spine would be a high bandwidth device with bunch of high gig port, 100 gig, 400 gig. So if any endpoint needs that amount of bandwidth, probably best place is to connect it to the spine. Obviously, you can design the network in any other way, but that could be the one. The other deployment would be a single chassis type of deployment. So I have a centralized space, kind of very, very similar to SDI world, and I connect all my endpoints into that single modular chassis in this kind of case. So what are the benefits of the spine leaf architecture? Is flexible. So I can build that spine network, spine switches in one location, and then I can distribute my leaf switches wherever it needs or wherever it's required. So if I have a big production network, I might distribute those switches through different studios, different production rooms. So that's one way. It's more complex because you need to understand what's happening inside of that network. So you would probably take some kind of tool, like some kind of network controller, to be able to help you with that. On the other side, if you go with single switch, single chassis switch type of deployment, you are more tied to a single space. So you have to get everybody to that single space. But your network configuration, it's more simpler. I have only one device to configure. I don't need to worry too much about who and how gets there. So, as I mentioned, spine and leaf architecture, one type of deployment could be like this. So I have two spines. I would create or connect my master control room to those spines devices because they're, say, nearby. And then I would have multiple studios, studio 1, 2, and 3, present in the system. And then I would have a control room to serve all those studios in this kind of case. So each of the control room could serve any of the studios. If I have a program in both of them, I could, in a nutshell, distribute to both of the control rooms and control it that way. But then let's look at another use case is that, let's say that I want to have my data center on same network. So I could connect my playout server, I could create a NAS or encoder. I still can do it in the same spine and leaf network. I would just dedicate a set of leaves to be connected to those endpoint devices and have or create my network in this kind of way. In this case, everybody is capable to reach everybody, and it still be a viable solution for IP broadcasting. So that's kind of one way. Everything is in the same location. But what's happening if you would go remotely, if you would have some remote production. So a smallest way to do this would be something like this, where you would have a remote leaf. What that remote leaf is that a leaf which is in a different location, serving specific needs of those location. Those could be miles away, kilometers away, and they would be connected through a dark fiber. In Cisco's implementation of spine and leaf architecture, you could still control the bandwidth over those links. So at no point I'll be able to send more than those links can support from that remote leaf. Or if I'm attracting any kind of traffic to this leaf, I will not ever send too much traffic, so I oversubscribe this leaf. So that's kind of benefit of it. Imagine that this is, I don't know, a TV station with remote studio, like on the other part of the town. So you would, and very, very small remote studio, you'll be able to do something like this. But what's happening if you, yeah, that's bandwidth management, which I mentioned earlier. So what if you would have multiple locations? So let's say that I have a studio in Amsterdam and studio in Brussels, and I want to exchange traffic between both of those studios. I'll be able to create two independent fabrics, interconnect them with dark fiber communication rather than dark fiber communication between those two studios. I'll be able to have PIM between those two and be able to have any kind of communication between them, any kind of exchange of the signal would be able to traverse over this infrastructure. So kind of point which I want to mention here is that you need to have PTP in this network, obviously to synchronize all of the endpoints. To synchronize all of those endpoints, you could do it through two independent GPS grandmaster clocks. Simple need is that both of the fabrics are synchronized to the same time, so they never get into asynchronous situation in this kind of case. So very important to synchronize PTP, not just between two fabric, but any kind of fabric which you may build in this kind of situation. And then you could expand network even over public internet or service provider network. So in this case, I do have Amsterdam, Brussels, London, and then Paris, all of them talking to each other. So as previously, Amsterdam and Brussels talk about over dark fiber, but then all four locations talk about around or with each other over the WAN network. So imagine this is a service provider somewhere in Europe interconnecting all four locations, so they will be able to exchange. Not just unicast, but also multicast. Sorry, not just multicast, but also unicast. They will able to stitch in this environment. What is important, if you would do this with Cisco, you will be able to control bandwidth exiting the fabric. So at no given point, you will be able to send more traffic than that link is able to sustain. So if you do have only subset of the bandwidth which is present on that link, you would just like take that information, tell it to network basically, and you will never subscribe it. So that signals could be traversed across the network in very reliable way, even though it's a WAN network basically. So let's look at a different use case of contribution. So let's say that we have a studio somewhere in Amsterdam, and then we have like arena or stadium, which is contributing with a signal. However, what's happening here? I'm getting signals. So I'm getting signals from Stadium, which are overlapping with my signals into the network. So what do I do there? I'm able to translate using network addressation, NAT, those information into something which is not overlapping with my network, and I'll be able to transport those over my network. So how do I do this? I do multicast NAT, multicast network address translation. How that works, I have a multicast NAT router. On the left side, I have a group which is 239.1.110, but that group already exists in my network, so I'll have something overlapping, which is undesirable situation. So on the destination side, I'm able to translate that group to 237.1.10.10. So this group is unique in my system, so I'll be able to transport it into my system. I'm not only changing the destination address, I'm changing source address, and I'm capable to change a layer 4 port as well. So the whole package information is changed, so it's completely unoverlapping with anything which I have in my network. So when those streams arrive, I'm changing S4 to G1 to S4 G4. So it's very, very unique and able to transfer that signals in the network which I have. So that's a contribution use case, signals incoming into the network, and how they are distributed through the network. There is also a distribution use case. So I do have set of sources which I have in my network, and I need to distribute them to 3 different service providers. So how do I do this? How do I do this without disclosing information about my network, and also protecting myself from security perspective? So as well, you can use multicast NAT, kind of similar situation. You would translate destination group, source IP address, layer 4 port, and you would choose a device like this device to be demarcation point. So it would be able to basically be a point where the translation happens and users cannot penetrate further into your network. So in this case, I do have S1, S2, S3, and I'm translating those into, oh no. Now you have the right diagram, sorry about that. So I have S1, S2, S3 translating into group 30, 40, sorry, 10, 20, 10, 20, and 30. So from that perspective, this information going off the demarcation point or that most left switch will be hidden to anybody listening on the other side, and I'm able to distribute those signals in a very secure way. So that's how we do translation from multicast to a different multicast address. So what will happen if you need to distribute that same content into public cloud? So challenge with the public cloud is that most of them do not accept multicast traffic, or not necessarily that's a standard thing, and they're way better coped with unicast traffic coming into public cloud. So how do you do this? Also, you might use public internet to do this. Public internet doesn't like multicast at all. You will not be able to transport a packet of multicast over public internet. So how do you do this? You would be able to translate that multicast traffic into unicast traffic. So you see that I have stream which is 239.1.110, but I'm translating into 192.168.110. So this packet will be able to go over public internet and end up in any destination which would accept that kind of traffic and that kind of network. So when we talk about public cloud, I'll be able to translate that sources, or S1, which I have here, into multiple unicast streams which are present here going to a different public cloud, if that's a use case, or simply different locations. So from that perspective, this traffic will be able to traverse public internet. And when it reaches public cloud, you will be able to route it to whichever service you want there and execute whatever you want to do. So at once you get a very easy way to do this contribution to a public cloud. So let's look at another use case, which is decoding the video in the stream. So what do we have here? We have a studio which wants a stream which is sent as a unicast. So if you want this to decoder to receive the stream, you would need to send 2 times same unicast stream. So both of them will require unicast stream from that source device. What that means, you send 2 different streams. That's very inefficient. I'm taking these 2 as an example, but imagine that you have 10, 20, or 100 of those. So each of them, you might not have even enough bandwidth to do so. So isn't it easier to just send a single unicast stream? And when it reaches the first hop in the network, you translate it into unicast. So that's what we do in our devices to have that, let's say, contribution or decoding video coming as a unicast to a first hop. Very efficient way to transport that and then decode it, or sorry, not decode it, convert it into multicast and then transport it through the network as a multicast stream. So how that looks like? Here we have a unicast stream which is 192.168.110. Incoming as a destination address, reaches the first hop, and that first hop basically translated into 239.1.110. So it's a multicast address. And then if I have these 2 decoders, they will be able to absorb that multicast stream, take it into the network, distribute it as a multicast, in a sense, very efficient, and send it to whoever is decoder. Another use case which you can solve with this multicast NAT configuration. So as I mentioned, like I started with the architecture of the network, you have a flexible choices. Either go with spine and leaf, satisfy a multiple studio type of environment, or go with a single switch, single modular switch. Let's say that's your OB-WAN use case, so you would put it there. So you have that. Then if you need to interconnect multiple geographically distant locations, so let's say that you have a remote production. Let's say that there is a sporting event like Olympic Games, for example, what happened in Tokyo. Somebody would take that signals which are coming from Tokyo, transport them into US, and then do all the editing and all the processing of the signals in the US. So they would have a minimal control room present into Tokyo, get all the signals, put them on the wire, get them in the US, and then do a further editing and everything else which you need to do. So that's kind of a value of that remote production in the system, and be able to interconnect multiple geographical locations, which is a value of IP, basically, IP signals. And then I hit the different use cases, contribution, distribution, where multicast NAT can be of help. So I receive a signal, I have an issue because it overlaps, I can translate that into something which will not overlap, or I need to have a distribution, but I don't want to disclose my information, or there is another problem which I want to solve, like there is a different time, kind of, you have a TDM, time division multiplex, at different time you need to have a different signal sent to a same group. So I'm able to kind of do that, mask that multiple signals in a single group and send them at a different times towards that destination. Then contribution to the public cloud, conversion from multicast to unicast type of streams, and then distribution or encoding, going from multicast to unicast, from unicast to multicast to do this. All this is available. If you go with the Nexus 9000, Cisco Nexus 9000 series of switches, they can cover all these use cases which are mentioned here. So take a look. And if you have any questions, please let me know.